we've been looking at this strange triangle, and we have noticed that despite how simple it is, there's lots in there, right? It's one of my favorite things, simple things that you can think about deeply. They're kind of like some of my favorite objects, and this is one of them. I'll give you a quick example of one we haven't looked at before. I want you to look at all the numbers that are there. I want you to have a look at, this time, we've thought about multiples in this before, right? For instance, last time we talked about all of the prime rows, except for the ones on the outside. In prime rows, all of the terms are multiples of that prime number. That's a bit weird, right? So for example, if I went down to the 13th line, right? All of the numbers in the 13th line, which we have a calculator we can check on now, right? For example, if I say, oh, 13C7. I have no idea what that number is, okay? Actually, well, I don't need to wonder what that number is. Let's just quickly work it out, okay? It's going to be, unless someone can beat me to it, 1,716, okay? And 1,716, if I divide by 13, is 132, right? So we've seen these weird patterns. There are more. I'll just quickly show you one. Let's pick multiples, but this time let's just look broadly, right? Let's have a look at, say, multiples of, you can pick any number, but being that I haven't drawn that much of it, I'm going to pick multiples of 3, okay? So if you look for where the multiples of 3 are, where's the first multiple of 3? It's 3, right? So I see one there, and I see one there. If I go down, I see another multiple of 3. Yep. Okay, now how far do you have to go before you see the next one?
15, 16.
There, right? Okay. High five for an attempt, but very no. I have symmetry here. Now, what's going on here? What's that about? Why have I got shapes like that? Okay, they are triangles. Let me do another one. That was multiples of 3, yeah? How about even numbers? I'm going to do them in boxes this time. Box. Where else? 4, 6, 4. Where else?
10. Then 626. 626.
It's a pyramid.
The 6
Huh.
the sixes.
I'm still going.
It's a sign from outer space.
What's going on? I'm seeing all these upside down triangles. Now, all of that to say, what I encourage you to do is draw more rows, or go back to where you've drawn, like I think I went up to 11 on one of the lessons, right? Go to where you see more and see how many patterns you can find. All of that just to prove to you that even though it's built in a very simple way, right? There are like it looks like you would only expect patterns between these two numbers and the next one's down. But the patterns go all over the place, okay? So in order to investigate one of the most important patterns, in fact, the pattern that gives us the binomial theorem, I could pick any of these rows, but I'm going to pick the 6th row. I think it's the easiest one that gives us a discernible pattern, okay? We're used to generating each of the terms, like when I actually go ahead and write the next line, okay? I write 1, and then I write 8, and 28, and 56, and so on, right? But the way I form the numbers as I look at this is I'm actually not paying attention to any of these numbers and how they relate to each other. I'm actually paying attention to the row above, right? But my whole point about noticing all these weirdo looking patterns is that there should be connections along the row. Like I should be able to, like without this row up here, I think I should be able to work out one number to the next because it's such a structured thing, right? So I'm expecting there's some kind of pattern here. So I'm going to look at row number 6 and see if there's a pattern, and then if I can identify one, I'm going to try to generalize, okay? So here we go. I'm going to name each of the terms here, right? I'm going to name them using the NCR notation that we introduced a little while back, right? I'm going to use the short form. So the first term should be like this, 6C0, right? Okay, so that's equal to 1. That's fine, we already knew that. I can write out all of the rest of the terms. Let's just quickly do that. The next one's going to be 6. I'm going to go all the way down. 15. 20. back to 15, and you're getting the picture. As we anticipated, you've got NC0, which is 1, and NCN, which is also 1. That was one of the first properties we noticed. Right? Okay, now what can we do with this? I was trying to suggest to you that not only can we look at the row above to generate the next row, I think we should be able to generate each term, each successive term, with all the previous terms. Okay? So, example. To go from here to here, term 0 to term 1. What's the difference? How do I do it? I can think about this two ways. I can think about this additively, right? So the difference from here to here is 5. The distance from here to here is 9. Distance from here to here is 5. And then it goes back down. 5, and then 9, and then 5. That's kind of interesting. That's kind of interesting, right? Gap of 5, gap of 9, gap of 5, 5 again, 9, and 5. That's kind of strange, but now I'm stuck. Right? I don't know what to do with that, okay? You might like to have a look at others and see if something else is there. But as I said before, one of the best ways to try and work and massage a mathematical problem is to look at it from another angle. Okay? So instead of looking from the angle of addition, I'm going to think about multiplication. Now before I do this, this should actually make sense to us, because how did we introduce this topic? We were looking at these guys. Right? And these are born out of multiplication. It's 1 plus x times 1 plus x times 1. So we ought to expect that multiplication ought to have something to do with this. Okay? So I'm just going to get rid of these for a second, because we're going to have a lot of information on there in a second, so the less the better. How do I get multiplicatively, I think that's a word, from this number to this number? What do I do? All I have to do is multiply by 6. Right? So it's 6 by 1. Yeah? Okay. How do I go from this term, 6, to this one? This is 6 times something. What's it times what?
2 plus 3. 2.5.
Yeah, 2.5.
Well, I mean, it's an easy way of doing it, is to say, well, it's 15 over 6, isn't it? Which I think is 2.5, okay? 15 over 6, I can write that a little simpler, right? I can write that as 15 over 6 is a fraction, bring it down. It's 5 on 3, right? 5 on 2. 5 on 2. That's the simplest way I can write it, which is the 2.5 you told me before. Yeah? Okay, let's go to the next one. I'm starting with 15. What do I multiply by in order to get to 20? I can either think of it as 20 on 15, or more simply, 4 on 3. I'm still getting bigger, aren't I? I'm going to write both of them. 20 on 15, which is 4 on 3. Are there any patterns there that you can see? Let's keep going.
Why is it creepy?
Okay.
Oh no.
Stay with me. Stay with me. Now, by this time, I've already gone as far up as I need to. Like, the rest of it is just symmetry. So you can tell me this just in reverse, right? This one's going to be 20 times what? 3 on 4. It's this, right? 15 over 20. This. 3 on 4. Right? What's this one? This is going to be that 15, right? Times 6 over 15, which we noticed before, that's 2/5. Right? 15 times 2/5. Okay. And then here, I've got my 6, and then I multiply by 1 over 6, and I can't simplify anymore. Okay, now, you're starting to see the pattern. You're starting to see it. If not, that's okay. I can see it easy because I've seen this hundreds of times. By the way, just a quick question. You saw we sort of went this way, right? I kind of skipped this guy because it's like, well, he's 1. But can you see there is something I can, what could I, like, I went the pattern down this way. So what would the pattern look like that way?
1 times 1.
1 times 1 and 6.
I'm going to leave him for a second. We'll come back to him. Because the whole thing about patterns is if they really work, they always work. Right? If you've really nailed the pattern. Okay? Now to make this even more clear, sorry I have so many colors on the board, but, right? Let me clarify this a little more. See how I've got 2/5 here, and then 3/4, and then 4/3, and then 5 over 2. That tells me this is not really a 1, is it? What should that really be?
6 over 1.
Haha, it's a 6 over 1. Thank you. Can you see it? Because look, this numerator, as I go up, is increasing, and the denominator is decreasing. Okay, here we go. Now I'm going to try and write this thing out.
I've seen this before. Yes.
This guy. This is 6 over 1 times 5 over 2. Right?
Oh, and then it's.
This is 6 over 1 by 5 over 2 by 4 over 3. Following?
Oh my goodness.
What's this guy? This is all of the previous ones. 6 over 1 by 5 over 2 by 4 over 3 times the new one. Okay, you can see the pattern now, can't you? What am I going to have here? 6 over 1, 5 over 2, 4 over 3, 3 over 4, 2 over 5. And then here, 6, 5, 4, 3,
2, 1.
2, 1.
And they all cancel.
Okay, now, you got heaps of cancelling here, which is why you ended with 1, right? I still haven't completed this picture yet, but that's okay. To help me complete it, I'm going to go one more step. Look at this. This is a disaster, right? Mathematicians hate writing more than they ever need to, particularly when there's a pattern you can take advantage
Oh
of,
my god.
right? So, for instance, let's pick one. How about this line here, okay? See how on the top there, I have 6 times 5, right? 6 times 5, okay? But we have learnt notation that makes it easier to write 6 times 5, knowing that what I really mean is just times the next one, etc., right? This starts like 6 factorial starts, doesn't it? It begins the same way. 6 by 5 by up, but then it stops. It's missing the 4, 3, 2, 1, right? So I'm missing 4 factorial. Do you agree with that?
Yeah.
So to write 6 by 5, I write 6 factorial on 4 factorial. Is that okay?
Yeah.
That's just the numerator. Now I have the denominator. What's the denominator? It's 2 times 1. It's 2 factorial. Right? Okay. Keep helping me. What's this? What's this numerator? 6 by 5 by 4. It starts just like 6 factorial, but what's it missing? It's missing the 3 factorial, isn't it? Right? It's going to be 6 factorial on 3 factorial. That's just the numerator. And then I've got 3, 2, 1. I've got another 3 factorial there. Okay, I can stop thinking, can't I? Can't I? Look, I've got that 6 factorial on the top, but I'm missing the 2 factorial over here. So I divide, and then there's a 4 factorial. Okay, 6 factorial on the top. I'm missing the 1 factorial. I know that doesn't matter, but you can see the pattern. 5 factorial.
6 factorial and
6 factorial on
0 factorial.
Ah.
Which is 1.
That is 1.
Aha. Now, I'm going to come back to that in a second. Before we address that, let's finish this thing. Let's finish this thing. If I've got 1 factorial, 5 factorial, 2 factorial, 4 factorial, etc. What's this? What's this guy? It should be 6 on,
5
factorial, 1 factorial.
which of course is just 6.
And the one above it is.
And this guy is 6 factorial on,
6 factorial times 0 factorial.
which of course is 1. Okay, now, remember I posed to you the question a little while back, and I said why? I said why? What? I mean, that's just weird, okay? No, it's not weird, it's the only result that makes any sense of this situation, right? Because if it's not 1, everything just explodes. It has to be 1, right? So, can you see the pattern?